Hello and welcome to the third and last session of the drone design workshop here at SimScale. My name is Milad and I'm very glad to see so many people who have joined for the last session of our journey through the world of simulation and drone design. Since this is the last session, I think you already know the procedure. I would like to make sure that everybody can hear me loud and clearly. So in the case you can hear me, please click the raise your hand button to show me that everything is working fine. Great, I see some hands. And just in the case for some reasons you might need it, we also have a toll-free audio service number. You can just call this number here, or a bunch of numbers for different countries, each of them are toll-free, and then enter this access code you can see here once you're asked to join the session. Okay, great, and let's take a look at our today's agenda. As usual, first of all, we will have a short discussion about the fundamentals of CAE and simulation. And this week we will focus on drop analysis, and we will investigate how or which stresses are occurring inside the drone if it's dropped. And this is a dynamic FEA simulation, so therefore we will talk about the fundamentals of dynamic analysis with SimScale. Then I also prepared again a live demonstration where I will show you how to set up yourself a simulation of a drop test. I will present your homework assignment to you, and if you have questions I will try to answer all of them. Okay, so let's start and talk a little bit about dynamic analysis. And last week we started to work on FEA static analysis, and the big difference between these two types of simulation is that dynamic analysis, unlike a static analysis, is used to get is used every time where you have a time-depending stress, displacements, and force fields. And usually this also means that inertial damping effects are included. And just to make sure that all of you get the difference, in a static simulation, all my loads are static. I mean, I can change them like we did in some other tutorials, but then it's they are like calculated or simulated as independent simulations. And in dynamic analysis, I don't have this pseudo time, but the real physical time. And this allows us to have, let's say, transient loads and boundary conditions, and also enables us to consider inertia and damping effects. We'll talk later about what inertia and damping effects are exactly. And basically, that's also a very good rule of thumb if you are not sure if you can, or if you should do a dynamic or static analysis. If you can't neglect inertia and damping effects, if they are important, you need to use a dynamic analysis. And if they are not important, you can use a static analysis instead. And you might also hear this in some thermodynamic courses, that static also can mean very slow changing, so slow in this case that inertia and damping effects does not need to be considered, but we'll take a look at the equations later. Here you can see a very good example for a dynamic simulation, and this is what we are going to do today. This is a drop simulation of a drone, and the color bars representing the stress inside the drone. And as you know, the maximum yield stress is around 40 megapascal for a drone, so since everything is in the green here, it should be fine. But if we start the animation, we can see that some areas become red. And here we should take a deeper look, because here it could probably crack. And basically dynamic analysis is relevant for all cases, or most of the cases, with immediate loadings, like dropping, punch tests, crash tests, etc. And another option is that you have a load which is a function of time and frequency. For example, a harmonic load. There you also need a dynamic analysis, even if the load is not immediate, but you need it since the boundary conditions and the forces and loads are time dependent. And another great thing about dynamic analysis is it allows us to capture the vibrational responses of the system. So in this case, if you take a look again at the animation, and it should start again. Yes, here you can see it's dropping and hitting the ground, and then we have this vibrational responses displacement of the drone arms. And these are things we can only capture with dynamic analysis. And damping can be very important for dynamic analysis, but it's mandatory. So it can include damping, and you need dynamic analysis that need to involve damping in your simulation. But you can also run dynamic analysis without damping effects. Okay, let's take a look at some kind of examples. And I would like to show you two very general examples which represents, let's say, the whole bandwidth of dynamic analysis. The first example is everything which we could sum up under the name high velocity simulation. So everywhere we want to simulate the impact of something, a collision or a drop. And a good example here is this drop of a mobile phone. And there are several kind of questions you might want to answer during the product design process, and where dynamic analysis can help. So this kind of simulation would answer some questions like, first of all, will the housing itself withstand the fall? And a very good criteria, therefore, is to take a look at the maximum stresses and to make sure that the highest stress inside the housing is smaller than the yield stress of the material it's made of. And also based off the results of the simulation, we can also find out, for example, if the display is likely to crack. For example, based on the displacement of the housing at the point. And we can also answer questions related to inner parts of the phone, like the question if the electronic part will withstand the impact. And another kind of example, which is also a good showcase for dynamic analysis, is everything related with frequencies in general, or especially high frequencies, especially everywhere where we have rotating machines, for example, or engines. But what I would like to show you today as an example for this kind of simulation is actually this steel truss bridge. I think most of you know this video. It's quite famous, where a troop of soldiers is walking on a bridge, and they are really marching in, let's say, with the same frequency. And since their marching frequency is matching with the eigenfrequency of the bridge, it starts to collapse. And so this kind of simulation can help us to find off if something will withstand a vibrational load, a specific vibrational load, and it will also tell us if it's dangerous if we have a match of frequencies, and if we match the critical frequencies of the part of the, in this case, a bridge. So, and now let's take to talk a little bit more about fundamentals. I don't want to tell you too much boring stuff about physics and show you too many equations, but I think at that point it could be quite useful to have at least a picture, a small picture about what are the backgrounds and basics of this kind of simulation. And therefore, let's take a look at this very generic example. This is a bar, which is on the left hand. Let me just use my pointer. On this left side, it's fixed, so it cannot move. And here we will have reaction forces and reaction torques. And just imagine to understand the difference between static and dynamic. A static simulation, there we would apply the load, and it would be at one time step. Here, for example, it's applied, and we would have this kind of linear ramp up and ramp down. And the big difference between static and dynamic is that in statics, the changes between these different load states are considered as so slow that everything will recover to its initial state after you remove the load. For example, here, we will have a displacement of this end. It will go down, we remove the load, and it will go up. In contrast to the dynamic simulation, just imagine it's a different material which is not very stiff, or we have use a hammer to apply a very fast dynamic load. What we would see here is that we don't have this linear displacement curve, but it's really a curve. And once the load is removed around here, when the hammer is not anymore in contact with the bar, it goes back with a different curve, and even the displacement changed into another direction, and we will have this vibrational dynamic response. And if you remember the session of last week, there we talked a little bit about the fundamentals, and there we basically just included this part of the term. Here you can see this governing equation of dynamic simulation. There we just covered displacement, stiffness, and the external force. Dynamic simulation is a little bit different. First of all, we have a physical time, and our forces and our loads and boundary condition can depend on time. And this also means that we don't only have a displacement, we basically also have to consider between the displacement, acceleration, and velocity too. And here it's basically the same part like in the static simulation. We have the stiffness or lateral stiffness matrix in the FEA model. We have the displacement vector, but here we again have a different additional term which is considering damping. And here what you can see, U point is the derivation of U. The derivation of displacement is velocity, and C is the damping. And in a larger model, in a 3D FEA model, this is represented by a damping matrix. And finally, we also include inertial forces, the inertial component, which you know as acceleration. And there we have the second derivation of displacement, which is acceleration. And we have M, which is representing the mass, or for a complex model, the mass matrix. And mass matrix, damping matrix, and stiffness matrix are part of the mesh later on. U is what U point, and U point. These three vector fields we try to calculate, and F from T is given. Okay, one very important point. Yes. You also see here this time history of deformation. What does it mean? Well, if you only have a linear body, then the force, this elastic force, is representing the time history of the deformation, and that's why we call it like this. But now I think let's try to take a deeper look at the terms of this equation. And as I mentioned, the inertial forces are any force induced by an accelerated mass. For example, if we take a look at the bar, it is the force induced by the acceleration of the mass of the bar. We have this damping force, this viscous damping, and basically what damping is dissipation of energy, similar to friction. And similar to friction, it converts kinetic energy typically to heat. And we have this elastic resistance, elastic force, which is based on the stiffness. Okay, then I would like to talk with you a little bit about dynamic responses and vibrations. If you take a look at the drone simulation, the drone drop simulation I showed you in the beginning, we had this dynamic response. And there are basically three kinds of dynamic response. First of all, we have force vibrations. And force vibration refer to a harmonic response. A detailed discussion about this is not really part of our webinar today, but we have a very nice FEA masterclass, another free workshop, which was already recorded, and you can take a look, and there you will learn a lot more about force vibrations. But just for the big picture, we have force vibrations, which means that we have all three components. We have the acceleration component, the damping component, the stiffness component, and very important, we have, that's why it's called force, an external force, which is forcing this vibration. And then we have free vibrations. Free vibration means that there is no external force which is like inducing these vibrations, and there we have a difference between damped vibrations and undamped free vibrations. And undamped free vibration basically means that we just don't consider any damping, we only consider the mass and of the model and the stiffness. And this kind of simulation, by the way, can be used to calculate the natural modes of the system. And the natural modes then are used, it's because you can calculate the frequency based off that. And this is the frequency where the system handles to oscillate under external influence. And so this simulation, this undamped free vibration simulation, is a very good starting point if you want to analyze if there is any danger coming from vibrational resonance effects. Okay, then let's talk finally about damping a little bit more in detail. And numerically, damping is represented by a ratio, where in this ratio is calculated by dividing the actual damping you have by a so-called critical damping. And the higher ratio basically means that the damp system is damped more. And the critical is by the critical damping. To explain it, it's a very good thing is to just imagine what it means. If the critical damping is your actual damping, then this ratio is 1. And if you take a look at how to calculate this critical damping, you might see this formula. A lot of textbooks, especially at universities and colleges, if you're going to talk about vibrations, there is this example based on a pendulum, or this example based on a spring and a damper, and the mass, which is and there you also get a similar formula like that. So it's, in this formula you have stiffness, the mass included, and overdamped means it's higher, and underdamped means it's slower. But what does it actually means? And therefore, let's take a look at this chart. So if something is critical damped, that's the fastest, let's say, way to damp the reaction. So here on the x-axis it's the time, on the y-axis the amplitude and here you can see if it's critical damped, it's starting at the top and straightforward going down. And if it's overdamped, it's going down slower, so but it takes longer at all. If you see, we are hitting this intersection with x-axis a little bit sooner than with critical damped, but then it's going in the wrong direction and back. And underdamped means that it's like with a lot of oscillations, but fast, and overdamped means it's quite slow, but without any oscillations. Okay, finally, let's talk about two things: time domain, and frequency domain. These are two terms I hated at college, at university, because I think it's very confusing, and these terms are also used in a lot of other professions like system design, etc. But in the case of finite element analysis and computer-aided engineering, let's try to bring some light into this. And time domain basically means that we capture the transient response of a structure to an arbitrary load. It can be any kind of oscillation, like we can see here. While frequency domain means that the response of this the structure responses to a structure of harmonic loads. And just to visualize it, this is a very example. We have like this sheet of metal. We are applying a force. And at the time domain load, at least the load can be represented as a function of time. For example, here it's also harmonic. But if we really do a simulation frequency domain, the load must be a structure of harmonic sinusoidal loads. But now let's do our live demo, and let's not talk about simulation types which we will not leverage today. And therefore I have for sure prepared something. So here again I have a project, and I'm quite sure, as you remember, last week I built up this project with you together from scratch, and since I don't want to waste your time with things you already know, I have prepared this project including everything: a mesh, the geometry, the mesh, the simulation, and the results, and I will just go with you through this project and comment a little bit so how I created it. So first of all, let's take a look at the CAD model. And for the CAD model, it's made of 3 parts. Again, it's imported from Onshape. And here you can see the first part here is the drone itself. So all the parts of the drone were merged to one body. I know that here we can start a discussion about the accuracy of the simulation. Our aim was to create a good introduction for you, and therefore we decided to simplify it a little bit. Basically, if you want to make it more complex, you can just split up the model and, like in some previous simulation, add some more details regarding the complexity of the assembly. And then it's just a little bit more of work for defining context, etc. Okay, so the solid one is the battery. That's the only part of the drone which was separated due to the large difference of weight and density. And the third part, solid 2, is the dummy for the floor. Okay, now let's take a look at the mesh. For sure, it's based on our geometry. And again, we use the TED dominant meshing with manual sizing. We defined a quite small range for the maximum and minimum element edge length between 1 and 3/10 of a millimeter. For the mesh grading, so like let's say the distribution of the mesh, we choose 2 for coarse, and we use first order elements since we don't want to investigate plastic deformation. If it's in the plastic deformation, it's already broken, and we don't allow any quadrangular surface elements. We have 2 refinements. First refinement is a local element refinement for the floor, making this floor much more coarse. You can see it here. It's really just two elements basically for this face, so 2 tetraeders. While here, based on the refinement 2 for the refinement zones, where yes, we have basically the lengths were divided by 10, we have much smaller mesh and some refinements, for example here where we expect to have some higher deformations, or here. Well, the meshing was finished quite quickly, and then the next step is to set up the simulation. But first of all, let's do a quick wrap up. So this is the simulation we're going to do today. By the way, we will simulate a drop test of a drone, as I mentioned. And yes, we are pre-processing, and I showed you like the first step would be to create and open a project, to import the geometry from OnShape, to create a new TED dominant mesh, and add some refinements. Next step is to set up the simulation. And first of all, we have to choose the type. And here we take solid mechanics, but dynamic analysis advanced instead of a static analysis. And then again, we have to define context. In this case, since the arm and the 2 parts of the chassis are already merged, we need other contacts. We have one general contact between the battery and the drone. It's a bonded contact with a tolerance of 1 millimeter. And as you can see, if I go on select assignment here, the battery is the master, and this upper face of the drone, which you cannot see because it's what split it before, is the slave. And we have a physical contact, which is important for really this unphysical, this standard contact. It will not consider any forces between a physical interaction, let's say, between the kinematic interaction of this part. And the physical contract, in contrast to that, will really allow us to resolve what is happening during this contact physically, and also will give us some information about forces, etc. And this is between the drone and the floor. And here we choose the floor as the master, since the slave is following the master and the master is not moving here. So that makes for this kind of simulation a lot of sense. And here we selected these 2 parts for the contact which will hit the floor. Great, then we had to define again some materials. We have no damping in the simulation included, but you could add it. And we have a material for the battery, which is a pseudo material just to add the weight. And we have ABS for the drone, and we have steel for the floor. Right. In this case, we also have initial conditions. The first one is the initial condition for the only initial condition we have basically for velocity in y direction, minus 10 meters per second. So in the simulation, it's not accelerated anymore. It's a constant velocity of 10 meters per second. And just one thing. Here on the model this time, we added volumetric load, gravitation, which means that we will have a little bit of acceleration based on the gravity. Well, and then we just have some boundary conditions, some constraints, no loads, and one of them is fixed floor, fixed support for the whole floor, so this whole floor cannot move in any direction, and we have a symmetry boundary condition, since we're using only a symmetrical part of the model. Great, then. Finally, we have to do time step definition. And here we did we defined the time step based on a CSV file which we've uploaded. And as you can see, until the time 0.0095 seconds, we use a difference time step which is much larger than the small time step we use from time 0.16. The reason is that during this initial starting phase of the simulation, before it actually has the first contact with the floor, not a lot is happening there, and this allows us to optimize the efficiency of the simulation. But everything which I showed you here is described in a step-by-step tutorial, which I will show you later. And then we can add some area calculation, like maximum displacement calculations for the propeller, or add a stress field for the drone. Right, and then we can very easily, for example, in this case, like vary the mass of the battery of the drone by changing the density. And what we did here is a kind of series of different simulation. First of all, let's do a quick wrap-up, and then we can take a look at the results. So, first of all, I showed you how to set up a project, and it's quite similar to the project we did last week. So we have to create a new project, and this time we will use dynamic analysis, advanced instead of static analysis. We assigned the mesh, defined contacts, physical contact as well as kinematic contacts. We defined the material, initial and boundary condition, which describe our interaction with the environment, and finally we started the simulation. Then let's take a look, and I have prepared some runs in advance. And this is the first run with the density of the drone battery of 2500, and it's already loaded into the online post processor. And what I will do now is to add a wrap by vector filter, but I will wrap it not by the and I will wrap it by the displacement. Apply. And now we can see how the geometry of the drone is moving and deforming. We have to refresh the view because it changed a little bit. And now I will hide the initial state. Go back to time step 0. And now change the representation from displacement to von Mises stress. And this, again, let's apply our good trick from last week, and here as the maximum data range for the color bar I will choose 40 megapascal, which is approximately the yield strength of ABS. And now you can see at time step 0 we have no stress and no displacement. Now let's start the simulation results, the playback, and you can see that now it's sitting, and now you can see that here everywhere we got hot spots of red, and here probably it could start to crack, and so we should take a deeper look at this. We also made some phase calculation, for example the propeller displacement in all directions, and it's here up to 10 centimeters. Right. Okay. And oh, one thing I would like to show you, I completely forgot about it, is that you can also take a look inside the simulation. For example, here we can go back here it's sitting. And now, for example, we can add a slice filter. And then we can take a look inside the part. Can take some time since it's a larger model. But you can see it here now. We have created a slice inside the drone. Great, and now I would like to talk with you about your homework for this week. This is the final homework. So the homework this week is about creating basically the same simulation I showed you during the live demo. We will again provide you with a very detailed step-by-step tutorial. Let's take just a look at it. Here, I will send a link with a recording tomorrow to you and the link to the step-by-step tutorial. Everything is described here, and if you have problems with setting up the simulation, you can just reply to this post in the forum and we will help you as soon as possible. And basically what you will do is you will investigate what happens if we change the mass of the battery and the motor and how this will change the maximum stressors. And therefore you should run 4 simulations with a 10% increased mass of battery and motor in each simulation based on the initial state of the simulation. As I mentioned, you will find a lot of help. And finally, now it's time, I think, for our Q&A. Thank you very much for joining us for this great journey. And if you have questions, just write them down and I will try to answer them. Samyak wants to know a little bit about the importance of choosing slave and the master. Very good question. So first of all, again, why do we need this context, this master and slave definition? If we have assemblies of several solids, we have to define how they interact with each other. Just imagine you have a gearbox, and if you don't define the contact between the parts, they will not be considered as interacting, and then you will not be able to simulate the effect you want to show. And slave and master, especially everywhere where I have deformation, it's important because when we try to calculate what happens between 2 time steps, what the code is doing, it's looking like, okay, the slave master phase moved in that direction or is now here, so how has the slave phase moved? So that they're still attached. And therefore, you have to be smart. A lot of cases, it's not important which you choose as a master or as a slave, but as for example for the floor, which is not moving at all, it's smarter to use it as a master. Okay, Bredon wants to know if we can dynamically script the time steps if for whatever reason we don't know exactly when the collision happens. For example, when it's not colliding 0.2 seconds, it's fine, but after collision you need 0.01 seconds. Brandon, that's possible. It's not completely automatically. I think I just showed it during the live demo, but let's show it again. So here on the simulation control, the only thing which you have to do manually is to calculate when it will hit it. For example, in this case, I think, yes, the distance is like 10 centimeters. No, that's more. It's the distance was like 10 centimeters exactly. And so after 0.095 seconds, it will be just before of dropping. Anwar Andrews wants to know, what kind of filter do you use to show the full body of the drone? I use the wrap by vector filter, and it's also described in the tutorial. Don wants to know if it matters which part is the master or slave. As I mentioned, it depends. A lot of cases it does not matter, but sometimes it can matter, especially if it's a complex content. If you have a lot of change, it can matter. And this is something based on experience. But usually the part which is larger or which is also mechanically following the other part should be the slave. Okay, great. I hope I answered all your questions. And thank you very much for joining. Oh, last question. Yes, exactly, Brandon. It's like you described it. Okay, perfect, sorry. So thank you very much for joining us. I hope you will all finish the homework in order to get certified. And I hope to see you as a new member of our simulation community. Have a nice weekend. See you soon. Bye.